I work on, Bacillus anthracis or anthrax, plague, tularemia, brucella, Q fever, B. malii, MRSA, E. coli. Many of these, in fact, represent clonal pathogens, and we can actually demonstrate that, in fact, their evolution matches a clonal pattern very, very well. So one of the metrics that I'll use quite a bit is a metric which I don't see on there, which is called the consistency index. You were introduced to that by Lance Price. So one way to think of the consistency index is how well does your data fit a clonal model. When it deviates from a clonal model, you get homoplazy, and there's several different reasons why you can end up with this. But the one that we see most often in bacteria is recombination. Now, another thing that we can do once we've figured out this hierarchical arrangement of these mutations is we can develop diagnostic markers. And so we've come up with this term that we call a canonical SNP. I'll tell you more about SNPs in a second. But for example, in this particular case, if we know a mutation occurs right at that position in a phylogeny, remember this is just a model, but it then is predictive. If you can then genotype at that particular location, you can then predict which members are a part of that subpopulation versus which ones are not. So I'll tell you quite a bit about canonical SNPs. We evolved this concept of canonical SNPs for a couple of reasons. The first one was just economics. It wasn't possible to sequence genomes of every isolate we had. It was much easier to go back and genotype them using a simple SNP assay based upon PCR. Nowadays, with whole genome sequencing becoming more and more affordable, we can in fact sequence large numbers of bacterial isolates and generate complete genotypic information and not rely upon isolated ones. But there's another reason why these are still useful, is that sometimes when you're doing environmental sampling or doing sampling in a clinic where you've got, a nasal swab or perhaps urine, you can go in and use PCR to amplify up very, very rare molecules and then genotype that. And if you have a very robust phylogeny and good sampling of your phylogenetic space, you can draw some pretty strong conclusions from even a single SNP or a series of SNPs. So in real life, the way we usually use these canonical SNPs is to have a battery of these at key phylogenetic positions, genotype across those, say a dozen or 20 of those across the sample, and from that then infer the location and identity of an unknown isolate. So of course the opposite of this is when you have recombination. And again, this is just a cartoon that illustrates that in fact DNA segments can move across different lineages. And when they do that, your consistency index starts to drop because you end up with characters, mutations, variation that are not moving in a clonal fashion and lower your consistency index. This happens a lot.